Okay, so greetings everyone once again. I'm really happy to see everyone on this webinar. My name is Orest and I'm Solutions Engineer at StarWind. Now, today our topic is the ZFS, where it was, current state, and basically tomorrow, what can we expect from it? So before I actually kick off, just wanted to make a short recap on today's agenda. So first, we're going to start with some brief ZFS history, what's it all about, its data integrity mechanism. Also, we're going to take a look at the ZFS structure, discuss the command RAIDZ types, how self-healing works. We're also going to see the main ZFS features such as snapshots, compression, and deduplication, what was new in OpenZFS 2.1, how it's used in the popular and known products, and of course, best practices and what to expect from it in the future. And in the end, we're going to have a short Q&A session where I hope I managed to answer your questions. So let's actually kick off. Now, ZFS has been originally developed by Sun Microsystems for the Solaris operating system in 2001. In 2005, the source code was published as open source as part of the OpenSolaris OS. In 2006, ZFS started porting to Linux, basically Fuse. In 2008, port to FreeBSD was released as part of FreeBSD 7.0, and at the same time, the development of the native Linux port started. However, since ZFS is licensed under the Common Development and Distribution License, which is incompatible with the GNU, General Public License, it cannot be included inside the Linux kernel. But of course, to get around this problem, most Linux distributions offer methods to install ZFS. Now, later on in 2009, Oracle basically acquired Sun and, well, decided that good stuff should not go for free. In 2010, the Illumos project forked the recent version of OpenSolaris to continue its development as an open source project. Now, in the 2013, which is another key date in ZFS history, the coordination of open source ZFS moved to an umbrella organization, OpenZFS, which allowed any person or organization that wished to use the open source version of ZFS to collaborate in its development and maintain a single common version of ZFS. So basically, what we know of OpenZFS project as today was founded in 2013. However, historically, OpenZFS has been implemented as a core ZFS code, with each operating systems team adapting it to fit into their projects and products. And this sometimes led to feature stagnation and significant divergence of features and command lines as different OSs developed different features and bug fixes, so often for a single platform rather than across them. And over time, the new feature development shifted from Illumos to Linux. These new features and fixes then had to be backported to Illumos before they could be reported to FreeBSD, and this was quite a difficult and quite a challenge maintaining different ZFS versions. However, in 2020, the OpenZFS 2.0 was released. It was known previously as ZFS on Linux and was earlier restricted to development of the module for Linux kernel, but after adopting the FreeBSD support, it became the main OpenZFS implementation, so no more Linux in its name. And therefore, both Linux and FreeBSD are now supported from the same repository, making all of the OpenZFS features available on both platforms. Now, so what's about ZFS? Now, zettabyte file system as it stands, or simply ZFS, is a 128-bit, which is much more than the common 64-bit file system. It allows for storing data of maximum 256 quadrillion zettabytes storage, and that's some good handicap for the future. But it's not actually the size of the ZFS why it's known for, rather the features and resiliency it provides. Now, first of all, ZFS is not just a file system, but also a volume manager. The obvious benefit of this is that you don't really need other tools to work with the storage. ZFS alone is enough to create a file system and combine your disks with adding resiliency and manage ZFS datasets to provide them as block storage or, for example, NFS or SMB shares. But let's stop in more detail on ZFS main benefit, basically resilience and data consistency. Now, ZFS is a copy-and-write transactional file system. Unlike common file system, it does not overwrite data in place, but creates new blocks instead. So the original data remains intact. Then the pointers are updated to look at the new block location rather than the old. And finally, only once the Uber block is updated to point to a new data, the old data is deleted to free up the storage space. And thanks to copy-and-write mechanism, there is no need in a journal, and therefore dual writes are avoided. But most important, we're not afraid of corrupting data during power outage, for example. Now, to be completely fair, the copy-and-write process itself does not guarantee data consistency. But if we are talking about ZFS, we can also see there is a transactional file system, which is based on the Merkle tree or simply hash tree. So ZFS manages all metadata and data as objects. So updates to all objects are grouped together as a transaction group. Whenever new data is written to ZFS, it creates a checksum for it. When the data is read, the checksum is verified. If the checksum doesn't match, then ZFS knows that an error has been detected and will then automatically try to correct it. In the very last step of writing a transaction group, ZFS makes the Uber block to point to the new change, which only then makes all new changes active. Until write is actively happening, Uber block points to the old data. So if power is cut during write, then the Uber block still points to the old valid data. And this means writes are basically, well, all or nothing. It can't happen that half of writes are written and the other half is missing. So as you'll already see, the ZFS storage pool is a tree of blocks. ZFS ensures fault isolation between data and checksum by storing the checksum of each block in its parent block pointer and not in the block itself. So every block in the tree contains the checksums for all of its children, so the entire pool is basically self-validating. Now, the only different and only special case is the Uber block because it has no parent, and corruptions to the Uber block are detected by the use of checksums inside the Uber block itself. So if the data and checksum do not match, ZFS knows that the checksum can be trusted because the checksum itself is part of some other block that's one level higher in the tree. And that block has already been validated. So this allows ZFS to detect silent data corruption. So if the data that is read does not match the expected checksum, ZFS will attempt to recover the data and provide good data to the application from any available redundancy, like mirrors or RAIDZ. Now that we understand the ZFS basis about the self-healing and data consistency, let's see just the basic ZFS structure. So I guess there is no need to explain that disks here are the actual, well, physical drives to which ZFS has direct access and needs it to ensure data consistency. So the very basic elements of ZFS are virtual devices, or simply VDEVs, and which can be composed of one or more physical hard drives allocated together. That's the level where we add resilience by using, again, mirrors or RAIDZ levels. Most VDEVs are used for plain storage, but there are, of course, special classes of VDEVs such as cache and log and others. The upper level is ZPool, which contains one or several virtual devices that appear as a single storage device accessible to the file system. There can be multiple, of course, ZPools on a single machine. And then you can further create Z volumes or additional file systems on tops. Now, Z vols are the actual block devices created from the ZPool storage space. For example, iSCSI or fiber channel target created to share with a different system, basically LAN. Datasets, or as named here, file systems, are a portion of space in a ZPool that basically emulate a traditional file system and can be used to segment storage for file-based access protocols like NFS or SMB. Now that we started the discussion about the RAIDZ also, let's take a look at the main levels. As mentioned already, unlike most file systems, ZFS combines the features of a file system and a volume manager. So this means that ZFS can combine a series of drives or a pool. Moreover, not just combine them, but of course to provide the resiliency. So the common configurations include the mirror, which is analog of RAID 1 with highest resiliency, which needs at least 2 drives. Stripe, pretty much obvious, no resiliency, same as RAID 0. And in case 2 disks are striped, half file will be written on disk 1 and the second half on disk 2. This of course provides maximum speed for read and write operation. And RAIDZ, basically RAIDZ 1, this level resembles the RAID 5 with a minimum of 3 disks needed, where 1 is used for storing parity, of course not the dedicated drive, and apparently 1 disk can fail, leaving the data safe. RAIDZ 2 and RAIDZ 3 options use 2 and 3 drives for parity. So for example, RAIDZ 3 can be a good fit for storing mission critical data, while RAIDZ 2 will be beneficial in terms of performance. Now, so how self-healing works in RAIDZ? We pretty much discussed it already, but if the data that is read does not match the expected checksum, the ZFS will attempt to recover the data, provide the good data to application and repair the damaged copy from any available redundancy. And that's what actually stays behind the RAIDZ self-healing. So suppose that an application needs some data blocks, and in those blocks, one of them is corrupted. As we know, ZFS is aware of this by checking the checksum of the block. If a checksum does not match on a block, it will look at any other disk in the mirror or RAIDZ to see if a good block can be found. If so, the good block is passed to the application, and then the ZFS will fix the bad block in the mirror or RAIDZ so that it also passes the checksum. As a result, the application gets the good data and the pool is in a good, clean, and consistent state. Now, let's devote some time to most common ZFS features. Now, the first I wanted to mention is the snapshots. So snapshots with ZFS are similar to snapshot with Linux LVM. A snapshot is the first class read-only file system as mentioned. It's a mirrored copy of the state of the file system at the time when snapshot was taken. So you can keep up to 2 in the power of 64 snapshots in your pool, and ZFS snapshots are persistent across the reboots, and they don't require any additional backend store. They use the same storage pool as the rest of the data, and a ZFS snapshot is also the copy of the Merkle tree in that state. So how does it actually work? Well, after taking a snapshot, new data is written to new blocks, but the old blocks are not reclaimed as the free space. The snapshot contains the original version of the file system, and the live file system contains any changes made since the snapshot was taken. So No additional space is used. Only as new data is written to the live file system, new blocks are allocated to store this data. Another feature is compression. In ZFS, it is transparent and inline if you enable it. So compression is enabled and disabled as per dataset or volume. And further, the compression can, of course, vary on the disk space saved. If the dataset is storing mostly uncompressed data, such as plain text log files or configuration files, the compression ratios can be massive. If the dataset is storing mostly compressed images and video, for example, then, well, of course, you won't see much of the benefit. Another ZFS feature is the deduplication. Now, ZFS uses block deduplication only. So block deduplication shares all the same blocks in a file minus, well, the blocks that are different. This allows storing only the unique blocks on the disk and reference the shared blocks in RAM. It's more efficient than byte duplication and more flexible than file deduplication. However, one of the drawbacks is that it requires some RAM to keep track of which blocks are shared and which are not. And since the duplication table is kept in RAM, if there is not enough of it, well, the duplication table will be read from the media itself, from the drive, and correspondingly bottleneck the performance. The overall and very general rule of thumb is to have 5 GB of RAM per 1 terabyte. Now, we recently all heard about the new OpenZFS 2.1 release. So let's actually take a look what's it all about. Well, first of all, it's compatible with FreeBSD 12.2 release and up, and Linux kernels 3.10 and up to 5.13. Now, this release offers several general performance improvements and as well as quite other completely new features. So first, that is the new compatibility property, which lets you specify the set of features that should be enabled on the pool. And this control basically makes it easier to create portable pools and maintain its compatibility between OpenZFS versions and across platforms. Now, the very famous new addition is actually the distributed RAID, or simply DRAID. It's an entirely basically new VDF topology. Now, when it was already pretty much complex, it's even more now. So when creating a VRAID virtual device, you specify a number of data, parity, and hotspot sectors per stripe. These numbers are independent of the number of actual disks in the VDEV. So a DRAID VDEV is constructed from multiple internal RAIDZ groups, each with data devices and parity devices. Now, these groups are distributed over all of the children in order to fully utilize the available disk performance, and this is known as parity declustering. Additionally, DRAID VDEV shuffles its child VDEVs in such a way that regardless of which drive has failed, the rebuild IO will be distributed evenly among the surviving drives. And this is really good improvement when it comes to faster rebuild times of DRAID comparing to a common RAIDZ. And it's also fair to say that distributed RAID VDEVs are mostly intended for large storage servers, and most of the design and testing was actually done on large disk systems. But it's fair to say that at smaller scales, the traditional VDEVs and spares remain, well, just as useful as they are. So what's about the ZFS in known and popular products? And here we mostly touch the NAS system. So I guess the most well-known one is the TrueNAS, which supports the OpenZFS file system and use it to ensure data integrity, checking to prevent data corruption. snapshotting, replication, and of course, various redundancy levels. So also to make this clear, there are several TrueNAS versions, and there is TrueNAS Core and TrueNAS Enterprise, which are based on FreeBSD, and TrueNAS Scale, which is based on Debian. However, all of them support OpenZFS 2.0, so no compatibility issues between these systems. The next is OpenMedia Vault. Now, unlike TrueNAS, natively, OMV neither uses nor supports ZFS. As a consequence, it basically cannot guarantee the high levels of data protection and integrity offered by native ZFS support. However, it can be installed with a plugin, but migrating and importing volumes from TrueNAS or FreeNAS, known previously, to OMV is a hard task and pretty much not supported. However, it's still a form of the integration of ZFS into OMV, so at your own discretion and at your own risk, pretty much you can try using ZFS on OpenMedia Vault. The next is the recently released StarWind ZFS. So it's based on Ubuntu version 20.04 and therefore has native ZFS support and is installed as the virtual storage appliance. The main idea behind StarWind ZFS, which has both free and paid versions, is to turn the existing and maybe aging hardware into the SAN or NAS and expose storage over such protocols as iSCSI, SMP, and NFS to other hosts. Plus, StarWind ZFS provides convenient installation process as well as recommendations for ZFS configuration depending on the number of drives. Now, the final thing I wanted actually to touch on this webinar are the best practices of ZFS and what to expect. Now, we already know that ZFS needs direct access to storage. So if a hardware RAID controller is used, and more often with the write cache, the additional failure point is introduced that can only be partially mitigated by additional complexity from adding flash to save data in power loss events. The data, however, can still be lost if the battery fails when it is required to survive a power loss event, or there is no flash and power is not restored in a timely manner. So, of course, hardware RAID will limit opportunities for ZFS to perform self-healing and checksum failures. So when ZFS does gain RAIDZ or mirroring, a checksum failure on one disk can be corrected by treating the disk containing sector as bad for the purpose of reconstructing the original information. This can be done, however, when a RAID controller handles the redundancy on its backend. So otherwise, the HBA card should be used instead. Now, the most, I would say, expecting features of ZFS is the ability to extend RAIDZ by simply adding more drives to the VDEV. So currently, as you probably know, ZFS is extended by adding new VDEVs. So technically, you can add a single drive VDEV to your RAIDZ, for example, RAIDZ1 or RAIDZ2. However, it will act as a single point of failure. If that single drive VDEV fails, well, you lose your data. Otherwise, you have to add the VDEVs with the same resilience type, or replace drives one by one with the larger capacity. This, of course, significantly limits the ZFS as to its scalability, convenience. So it was already planned the RAIDZ extension to be included in OpenZFS 2.1, however, did not manage to yet make it into its release, and as known, it is expected to be added in the next upcoming major ZFS release. And due to ZFS peculiarities, it actually becomes a perfect fit for archival, file, backup storage, and also the media storage. Now, at this time, I would be more than glad to answer your questions, so please feel free to ask them. And another question from Alexander, which is the most efficient benefits, ZFS versus XFS? Well, I would say that first of all, XFS, well, when comparing to ZFS, well, let's start from the other way around. So ZFS is built around the cornerstone of reliability, while XFS, I would say, is built more around the performance in terms of parallel I/O. When it comes to features, again, the ZFS has its own RAID implementation, like RAIDZ mirroring, so you can have the redundancy on a software level, which is pretty much superior to any other software or hardware RAID solution. And also, if we're talking about the features themselves, I would include built-in compression algorithms like LZ4 and gzip, for example. However, the main plus of XFS would be basically the performance from my point of view. It's optimized for huge files and for parallel I/O, and this makes it easier choice when the higher performance is required. And another question, should I use virtual SAN? Well, if it's from StarWind, well, definitely. Okay, so I believe we'll be rounding up this webinar. So I would, first of all, take one more question because I see currently using hard SAN. Well, virtual SAN is beneficial in terms of the hyperconverged infrastructures and when you're really wanting to avoid a single point of failure, which is the single hardware sandbox. So when you're relying on the single hardware sandbox, well, it's still the single point of failure. So distributing and sharing the storage, providing high availability between the nodes in the cluster might be and actually is much better in terms of the reliability and resilience. Okay, so thanks and huge really thanks everyone for dedicating your time to come to this webinar. I hope you enjoyed it and had some useful information on this. Thanks everyone for the questions. In case I missed them, because I might have, we will also answer them in the upcoming webinar on our next plan. And again, thanks everyone. Wish you a great day or evening whenever you are. And of course, to stay safe. Goodbye.